Hi, everyone, and welcome to our introduction to limits. First, we'll give a rather intuitive definition of what limit means. The statement, the limit of f of x as x approaches c equals L, means that we can force f of x to be as close to the real number L as we wish by making x sufficiently close to the number c. If we want f of x to be very close to L, then it stands to reason that we'll have to make x extremely close to the real number c. And by the way, this real number L is the limit. So we can force f of x to be as close to the limit L as we want just by making sure that x and c are sufficiently close together. So how close are we going to make f of x and the limit L? Within epsilon units. And this thing right here is an epsilon. I'll write it over here. We'll see that a lot in real analysis, so this is one of those things that we want to memorize. So we can make f of x within epsilon units of L. And by the way, this real number epsilon is understood to be greater than 0. And it's also understood that epsilon is going to be a very small positive number. If epsilon were a large positive number, and f of x and L were within epsilon units of one another, that wouldn't mean very much. Epsilon is 1,000,000. F of x and L are within epsilon units of one another. That is, they're within 1,000,000 units of one another. Well, so what? That doesn't mean they're close. If epsilon is small, maybe 0.000001, and f of x and L are within epsilon units of one another, then they are very close. So it's understood that epsilon is a positive real number and very small, arbitrarily small. And we can make f of x and L as close as we want together by making x sufficiently close to the number c. Well, how close is close enough? How close does x have to be to the real number c in order for f of x to be within epsilon units of L? We require that x be within delta units of the real number c. And just like epsilon, delta is greater than 0. And I'll identify this delta over here too. Now, let's come out and say something that will be obvious once we mention it. The closer that we want f of x and L to be, or let me say this, the closer we want f of x to be to the limit L, it stands to reason the closer x has to be to the real number c. If we want f of x to be very close to L, then x has to be very close to the real number c. So this delta, where delta is within, where x is within delta units of C, this delta has a value that has to depend on the value of epsilon that we've chosen. If epsilon is not a very small number, then x and c don't have to be that close together, and delta won't have to be a very small number. But if we want f of x and L to be really close together, within epsilon units of one another, where epsilon is a very small real number, then x has to be really, really close to c. So this delta has to be a very small number. X has to be within delta units of c, where delta is going to be a very small number. The point I'm making here is that the value of delta depends on the value of epsilon that's chosen. We choose a value of epsilon first, or assume that a value of epsilon has been chosen. And then we choose delta accordingly. Now, I will define this more precisely right now. Okay, here's a more precise formulation. The statement, the limit of f of x as x approaches c equals L, means that given an epsilon greater than 0, and it doesn't matter how small this epsilon is, given any real number epsilon greater than 0, no matter how small, there exists another real number delta, which is a function of epsilon greater than 0, such that the distance between x and c less than delta implies the distance between f of x and L is less than epsilon. So if this is how close we want f of x and L to be, then all we have to do is make x sufficiently close to c, less than delta. Now, there's something slightly wrong with this definition. I didn't want to put it in initially, but I'll call attention to it now. When we say that we can make f of x as close to L as we want by making x sufficiently close to c, we mean that we can make f of x as close to L as we want by making x as close to c as we want. X can be as close to c as we want without actually becoming equal to c. So there's a technicality here. We can make f of x as close to L as we want, provided we make x as close to c as necessary without x actually becoming equal to c. So let's see, if x were equal to c, then x minus c would be 0. But we don't actually allow x to be equal to c here. And so to make sure that doesn't happen, we're going to put this in as part of our formulation. This part guarantees that x and c are never equal. We can make x as close to c as we want without x actually becoming equal to c. So this is the definition of limit. And now that we have that definition, let's do a few exercises. Okay, here's a nice easy one. We can actually compute this limit by plugging in the number that x approaches, in violation of what I just said. But if we plug 2 in, we get 4 plus 4 is 8, minus 6 is 2. That's our limit. Let's prove that this is the limit using the definition of limit. And here's how we do it. the first thing we do is we throw out the challenge. Let epsilon greater than 0 be given. And essentially we're saying, give us a positive epsilon. I don't care how small it is, but we can make f of x in this limit within epsilon units of one another. And by the way, maybe it wouldn't be a bad idea for me to identify my f of x and identify my limit. We've thrown out the challenge. You can pick any positive epsilon you want. I don't care how small it is. We can make f of x in this limit 2 is closer than epsilon units together, just by making x sufficiently close to 2. So we've thrown out the challenge. We assume somebody's given us a value of epsilon. And so now we supply the value of delta. And you know what? I don't know what delta should be. If we look at a proof of an example like this in a textbook, they'll have the value of delta here. They'll have what delta should be. We'll have no idea where it came from, but in a textbook, they'll have a value for delta, and that value will work. Well, it's time for me to choose a value of delta, and I don't know what delta should be. Well, we're going to unveil how that value of delta is selected. What we don't see in the textbooks is that there's some scratch work that's done, aside from what's provided as the proof or submitted as the proof. And what I'm going to do right now is designate some of my workspace as scratch work. And I'll write down what I want. We want delta greater than 0 such that x minus our limit 2 less than delta implies that x squared minus 3x plus 4 is within epsilon units of 2. So here's my f of x. Here's my limit L. And I want delta such that x minus 2 less than delta tells me that f of x minus L is less than epsilon. That's what I want. Now, how am I going to get this delta? I don't know yet, but I'm going to keep working. And I'll just do some scratch work because that's what this is, right? So we'll have x squared minus 3x plus 4 minus 2, absolute value. And I'll combine the constants here. X squared minus 3x plus 2. And this thing can be factored. This thing is equal to what? X minus 1, x minus 2, is that right? Let's see. Minus x minus 2x is minus 3x. Yep, that's it. Okay. Now, what am I going to do with that expression? I know something about x minus 2, absolute value. So I'd kind of like to isolate x minus 2 in its own absolute value. and use the fact that absolute value of x minus 2 is less than delta. So here's what I can do. I can break this up into the product of absolute values and the reason I can do that is that the square root my foot, absolute value of AB is equal to the absolute value of A, absolute value of B, for all real numbers. So I have the right to split these two up into their own separate absolute values. And this thing, I know that that's less than delta. But what about x minus 1? I don't know anything about x minus 1. So I'm going to have to make a supposition here. X has to be close to 2 in order for f of x to be close to L. So this delta can't be a large number. We want delta to be small so that f of x and L will be within epsilon units of one another, no matter how small epsilon is. So delta is going to be a small number. How small? Well, we don't know yet. But we want x and 2 to be close to one another. So x minus 2 has to be small. We know that much. We don't know how small, but x minus 2 absolute value has to be small. So I'm going to use one of these magic phrases that we see in math. Without loss of generality, delta is less than or equal to 1. We want delta to be small, so we're sure it's going to be smaller than 1. So we'll just say, hey, we know it can't be any, we're not going to have delta any bigger than 1. So we'll just say, without compromising the integrity of our proof, that delta is less than or equal to 1. And so that means x minus 2 absolute value is less than delta, which is less than or equal to 1. And that means that x minus 2 is less than 1. Now, there's a property of real numbers. We might remember this. Hopefully we do. Absolute value of x less than r, if and only if negative r is less than x, less than positive r. We're going to apply this principle to this inequality so that we can get rid of the absolute values. There, I just got rid of the absolute values in this inequality. This inequality tells me something about x minus 2. I don't want to know about x minus 2. I already know about x minus 2. I already know that absolute value of x minus 2 is less than delta. What I want to know about is x minus 1. So I'm going to manipulate this inequality so that it tells me about x minus 1. And how do I do that? Well, I think if I add 1 to all three sides, I'm going to get x minus 1. So that's what I'll do. I'll add 1 to each side. And that tells me something about x minus 1. With my assumption that delta is less than or equal to 1, x minus 1 is positive and something else. It's less than 2. It's a positive number less than 2, which means absolute value of x minus 1 is less than 2. Now, let me get back to where we were. And I'm going to erase some of my scratch work because I'm out of board space. But in the exercises that we do, what we should do is set aside a space on our sheet of paper. And we don't want to erase any of our scratch work. We want to keep our scratch work, and we want to submit our scratch work with the proof. I'm only erasing part of the scratch work because I'm just out of board space, that's all. So I'm going to go up top and sort of continue from where I left off. I'll say observe absolute value of x squared minus 3x plus 4 minus 2 equals dot, dot, dot. X minus 1 absolute value, x minus 2 absolute value. And see, this is exactly where we left off. This is where we got stuck. We knew that x minus 2 was less than delta, but we didn't know what to do with this x minus 1 until we got down here. And we found out that absolute value of x minus 1 was less than 2. So this is less than 2 delta. Now think about it. In our proof, aren't we going to try to make f of x within epsilon units of the limit 2? In other words, aren't we going to try to make f of x minus 2 less than epsilon? Over here, here's my f of x. Here's my limit. Aren't we trying to make f of x within epsilon units of the limit? In other words, we're trying to make the absolute value of f of x minus the limit less than epsilon. Well, we have absolute value of f of x minus the limit less than something right here. So why don't we make this our epsilon? We're going to make this our epsilon. Oh, that's great. Now I'm going to have to destroy a little bit more of my scratch work. If I were doing this on paper, I wouldn't erase anything. I'd just make all of this part of my scratch work, which I would submit with my proof. So let's see what we conclude. We conclude that epsilon is going to be equal to 2 delta. Aha! So that's what delta is supposed to be. Delta is supposed to be epsilon over 2. But I did make another assumption on delta earlier on, didn't I? I said without loss of generality, delta is less than or equal to 1. So in order to make this proof work, delta either has to be the smaller of epsilon over 2 or 1. So that's what I'm going to put here. Delta is the minimum of epsilon over 2 and 1. And by the way, at this point in my scratch work, I denote this is the end of my scratch work, and I encapsulate all of my scratch work in a box so that anyone else reading my proof will know that this is scratch work and not part of the actual proof that I'm submitting. But it should accompany the proof that I'm submitting. That's why I don't erase my scratch work. I submit my scratch work with the proof. And now, because I need the board space, I'm going to erase my scratch work, which is something that I would never do if I was writing this out on paper. I would keep my scratch work. I would submit it as supporting evidence to my proof. Okay. We'll let x minus 2 be less than delta, where delta is formulated this way. And here's our function, x squared minus 3x plus 4. And here's our prospective limit, 2. And what we're doing now is largely a repetition of what we did before. We'll combine the constants, and we'll get absolute value of x squared minus 3x plus 2. And we factor that, x squared, let's see, how did that factor now? X minus 1 and x minus 2, I think that's right. Negative x, negative, yep, okay. I've factored the polynomial. I have the absolute value of a product, which we know to be the product of the absolute values. And I might justify this. Absolute value of AB is absolute value of A times absolute value of B. And x minus 2, that's less than delta. And we know that x minus 1 is less than 2. So this product is less than 2 delta. And what is delta? It's either epsilon over 2 or it's 1. So I'm going to say less than or equal to 2 epsilon over 2, which equals epsilon. Technically, my proof is done. But for the sake of my readers who may be on automatic pilot, they may be following my proof point by point without seeing the big picture. And sometimes we do that. We follow every step of the proof, and when we get to our destination, we don't know that we've arrived. So what we're going to do is we're going to tell our readers what it is we just told them. See, isn't that what a good speaker does? He tells his audience what he's going to tell them. Then he tells them. And then he tells them what it is he just told them. And that's where we are right now. We're telling our audience what it is that we just told them. So here's what we told them. X minus 2 less than delta implies our f of x minus our prospective limit is less than epsilon. That's what we just established. Now, when our reader sees this, they're going to wake up and say, what? And they're going to go through the steps that we just went through, and they're going to say, oh, that's right. Yes, that's exactly what they did. They showed x minus 2 less than delta. It implies f of x minus L is less than epsilon. Yes, I see it now. That's exactly what they did. Our readers are with us now. And so we can claim that we have proved what we set out to prove. Namely, that the limit as x approaches 2 of this function f of x equals x squared minus 3x plus 4 is equal to 2. Very good. That's our proof. Now time for another one. Okay. This is a nice exercise. There's a little bit of a challenge here. We're computing the limit of a cubic polynomial. So our f of x here is x cubed minus 3x plus 4. And here's our limit, 22. We start our proof by throwing out the challenge. Let epsilon greater than 0 be given. Give me an epsilon, a positive epsilon, I don't care how small it is, we can make this function within epsilon units of that real number. So a challenge arises, they give us an epsilon, and so now we say, let delta, which is a function of epsilon, greater than 0, be given by, oh my goodness, I'm in that situation again. It's time for me to say what delta is, and I don't know what delta should be. Well, that's okay, because you know what? At this point in the proof, I'm not supposed to know what delta is. This is something that I have to figure out through scratch work. This is the part of the proof that we never ever see in a textbook, and yet this is the heart and soul of the proof right here. This is where the real strategy goes. Never see it in a textbook, but the person who does the proof that's in the textbook has done scratch work just like we're doing. It's just that we never get to see it. When we read the proof in a textbook, we see delta given here, and we just think, oh, they figured it out just like that. It's not the way it is. We've got to do our scratch work. And the scratch work that we do for a proof like this is every bit as important as the proof itself. So we don't throw the scratch work away. We keep it, and we submit that with the proof as supporting evidence. So let's say what it is that we want. we want delta greater than 0 such that x minus 3 less than delta and greater than 0 implies that our function x cubed minus 3x plus 4 minus our prospective limit 22 is less than epsilon. That's what we want. And again, it wouldn't hurt to label our main characters here. I'll do it right here. I'm going to say observe and we have our function x cubed minus 3x plus 4 minus our prospective limit f of x L, and now I'll just combine the constants. So we have x cubed minus 3x, 4 minus 22, negative 18. Sure, it would be nice if we could factor this like we did the polynomial in the previous example. Well, you know, it turns out that we can. And hopefully after I do this proof, I'll tell you why it is that we're always going to be able to factor this thing. Not only that, but it's going to be the case that x minus the number that x is approaching is always going to be a factor. Oh, I hope I'll write it down over here. Okay, I just wrote myself a reminder on the adjacent board. I guess I wrote myself a sticky board. This thing can be factored. X minus 3 is going to be a factor. No, I'm not psychic. There's a sound algebraic reason why this is true. But you know what? If I know what one of the factors is, the other factor is going to be very easy to figure out. Whatever goes here has to be such that when we multiply it by x, we get x cubed. Well, let's take a wild guess and say x squared. Now, whatever goes here has to be such that when we multiply it by negative 3, we get negative 18. So I'm guessing that that's plus 6. The only term that's in doubt is the middle term. And remember how we're getting everything else? This thing times this thing has to equal this function. And let's look at our function. Notice that there are no x squared terms here. Okay. So there's 0x squared here, which means that whatever goes here has to be such that when I multiply these two things together, I get 0x squared. But you know what? When I multiply this by this, I get negative 3x squared. So whatever goes here has to be such that when I multiply it by x, I get a positive 3x squared, and the two add up to 0x squared. So whatever goes here has to be such that when I multiply it by x, I get plus 3x squared. Okay, It's going to be plus 3x. And just to double check, I'll make sure that the rest of the polynomial works out just fine. I'll make sure that everything works out, not just the second degree term, but we'll vouch for this term as well. We have a negative 3x here. So let's make sure that's what we get when we multiply these two things together. Negative 3 times plus, negative 3 times 3x, that's going to be negative 9x. And x times 6 is plus 6x. Add them together, we get that negative 3x. Okay. Beyond a shadow of a doubt, we've done this correctly. We've factored it correctly. Now, can this thing be factored? I don't know. But I'm not really that worried about it. Whether I can factor this thing or not, I'm going to be able to pull this proof off. I have the product of two polynomials, absolute value. So I'm going to split this up into the absolute value of the first times the absolute value of the second. And this thing, x minus 3, I know that's less than delta. And this thing, I know that this is, I don't know anything about this. Not to worry. We were in this same situation in the previous proof, weren't we? So we're not in a position that we haven't been in before. And when we were in this position before, we knew exactly how to deal with it. Do you remember what it was that we did in the last proof that allowed us to put an upper bound on the absolute value of this thing, the unknown? But we made a supposition, one of these without loss of generality things. So let me do that again. It worked last time. I'll say without loss of generality. Which means essentially that we're not in any way sabotaging the integrity of our proof. This assumption will in no way invalidate our proof. So without loss of generality, what was it that we said? Wasn't it that delta was less than or equal to 1? Wasn't that our assumption? We'll do the same thing again. By the way, is there anything special about this one? Not really, other than it's a nice, easy number to work with. Almost certainly, delta is going to be less than 1. With absolute certainty, delta is going to be less than 1. So we pick 1 as a nice, safe number that's easy to work with. Well, let's see. X minus 3 is less than delta, which is less than or equal to 1. And that implies that x minus 3 is less than 1. Now, do you remember the trick that we used in the last proof to deal with this? We had this absolute value theorem. And the theorem didn't seem like much at the time, not a big deal. But absolute value of x less than some positive number r implies, well, I'll tell you what, I'll have to write it down here. absolute value of x less than some positive number r, if and only if negative r is less than x, which is less than positive r. We're going to apply this theorem to that expression. And here's what we get. Negative, see, this is our r right here. So we're going to get negative 1 less than x minus 3 less than positive 1. Now, you know what? In the previous proof, we had a factor of, what was it? I guess it was x minus 1. And so we added the right number to all three sides and got x minus 1 sandwiched in between 0 and 2, I think it was. Well, we don't have an x minus 2 here or an x minus 1 here. So what I'm going to do is I'm going to use this inequality to get an upper bound on the absolute value of x. I'll add 3 to all three sides. And I'll get 3 plus negative 1 is 2. 3 plus x minus 3 is x. And 3 plus 1 is 4. Now, what can I conclude from this inequality? X is positive here in this inequality, so x and absolute value of x are one and the same thing if x is positive. So this tells me the absolute value of x is greater than 2, it's less than 4. And we're interested in the upper bound on the absolute value of x. So this tells me absolute value of x is less than 4. That doesn't seem like it's going to be very helpful, but trust me, it's going to be very, very, very helpful. It's going to be exactly what we need for this exercise. And here I go again, erasing some of my scratch work because I need board space. But I would never, ever do this if I were writing this on paper. So we pick up where we left off. And let's see what we had. We had f of x minus L, right? So we had absolute value of f of x and we made it all the way to this spot right here. Absolute value of x minus 3 and absolute value of x squared plus 3x plus 6. And that's when I hit the chicken switch and said, I don't know what to do next. But I know now. I know exactly what we need to do. I know that this is less than delta. So this is not of concern to me right now. I need to put an upper bound on this. And here's what I'm going to do. I'm going to write the first absolute value. And I'm going to take the second absolute value and break it up into 3 terms. Now, what gave me the right to do that? So, the triangle inequality. But it does say inequality here, doesn't it? So I'm going to have to put a less than or equal sign right there. And I'll simplify the contents of this thing a little bit more. X minus 3. And absolute value of x squared, that's the same thing as the absolute value of x quantity squared. This is the same as 3 absolute value of x. And this is 6. Now I'll pull my less than deltas and all of that sort of thing. X minus 3 less than delta. Now remember, absolute value of x was less than 4. All of a sudden, this is a very helpful observation because this thing is less than, well, this thing is absolute value of x squared. So absolute value of x squared is going to be less than 4 squared, or 16. And absolute value of x less than 4, we have 3 times that. That's less than 3 times 4. So let's see, 16 plus 12 is 28, plus 6 is 34, less than 34 delta. Well, what were we trying to do? Weren't we trying to take this thing, f of x, and the limit 22? Weren't we trying to make the absolute value of their difference less than epsilon? Well, we have the absolute value of their difference less than 34 delta. We got the absolute value of their difference less than something. Let's make this something our epsilon. So delta equals epsilon over 34. Oh, wait a minute. We also said that delta had to be less than or equal to 1. So just in case, by some bizarre twist, this thing turns out to be greater than 1, we'll do this. Delta is the minimum of epsilon over 34 or 1. And that concludes our scratch work. We don't destroy it, we save it, we submit it with our proof. And this will make our proof very easy to follow, unlike the proofs we see in the textbook. And I am erasing this scratch work only because I need the board space. Okay, I got my delta. I'll continue my proof. Here's my f of x minus my limit. And let's see, I will get this garbage minus 18, right? Oh my goodness, I wish I had not erased that factorization. But I do know that x minus 3 is a factor. And I had an x squared plus 6, I think, let's see, negative 18, yep. Okay, now I want to get 0x squared. This gives me negative 3x squared, so this product must give me positive 3x squared. Excellent, okay. And now I split it up into two absolute values. And this thing I split up using the triangle inequality. That seemed like a pointless theorem when we went over it a couple of weeks ago. But now it turns out to be very important. So absolute value of x squared, or rather I'll do it this way, plus absolute value of 3x plus absolute value of 6. And I'll just note triangle inequality. And this thing, absolute value of a product, equals the product of the absolute values. Okay, and now I will simplify what I have just a little bit more. X minus 3. And I have absolute value of x squared, but that's the same as the absolute value of x quantity squared. And absolute value of 3x is 3 absolute value of x. Less than delta. X squared is less than 16. 3x is less than 3 times 4, less than 12. And what did that amount to? Let's see, 28 plus 6 is 34. 34 delta, which is Do I need an equal sign there? I sure don't think so, because this is less than delta. This is less than 16. This is less than 12. No, I need less than right here. And 34 delta, that's less than or equal to 34 epsilon over 34, which is epsilon. Technically, I'm done with my proof, but as a courtesy to those people who are watching and going along point by point, and who may not have realized that we've arrived at our destination, I'm going to tell them what it is that I just told them, just as a courtesy. And I will say this. All of us need that courtesy extended to us at one time or another. So where did we start out? We had x minus 3 less than delta. And what did that give us? It gave us this thing, absolute value of x cubed minus 3x plus 4 minus 22. This thing turned out to be less than epsilon. There. We just told them what it was that we told them. And now we're going to tell them what all of this means. The limit as x approaches 3 of x cubed minus 3x plus 4 is equal to 22. End of proof. And I just remembered I am supposed to tell you how it is that we know that this monstrosity that we get right here can always be factored. And x minus the number that x is approaching is going to be one of the factors. There's an algebraic reason for that, and I'm going to tell you this right now. Okay, dirty tricks here. Suppose we have a polynomial, p of x, and the limit as x approaches c of p of x equals L. I claim that the polynomial p of x minus L is going to have x minus c as a factor, and here's why. Suppose that p of x is a polynomial, and the limit of p of x equals L. Well, how is it that I figured out that the limit of p of x as x approaches c equals L? I took this number and plugged it into the polynomial. Polynomials are continuous, which means we can compute their limits by plugging in the number that x is approaching. So, what that means is that if I can compute p of x, if I can compute the limit of p of x by plugging in L, that means that the polynomial evaluated at c is equal to L. Okay. And this means that the polynomial evaluated at c minus L is 0. Hence, given the related polynomial, p of x minus L, and this is a polynomial. All we're doing is we're taking this polynomial and subtracting a constant from it, so it's still a polynomial. Given this related polynomial, when we plug in c for x, we get p of c minus L, which equals 0. So in other words, p of x minus L is a polynomial that equals 0 when evaluated at c. And there's this theorem from algebra that says that if we can find a number to plug into a polynomial, and that number makes the polynomial 0. X minus that number is a factor. And it works the other way around too. Specifically, x minus c is a factor of this polynomial exactly when this polynomial equals 0 when we plug in c for x. So in other words, if we can plug in the real number c into a polynomial, and that makes the polynomial 0, then x minus that number is a factor of the polynomial. And this is true of any polynomial. Take a polynomial. If you can find a value of x to plug into that polynomial, x equals c, plug it into the polynomial, and that makes the polynomial 0, then x minus that number is a factor of the polynomial. Well, guess what? This polynomial is such that when we plug in c, we get 0, which means that x minus c is a factor. So let's apply this to the previous exercise. I made this exercise up. How did I know that this was going to be the limit of the function as x approached 3? I just took 3 and plugged it in for x, and I got 22. So when I plug 3 into this polynomial, I get 22. So what am I going to get if I plug 3 into this polynomial? Well, if I plug 3 into this polynomial, I get 22. So if I plug 3 into this polynomial, I'm going to get 0, which means that x minus the number that I plugged in is a factor of this thing. And when I simplify this out, I have x cubed minus 3x minus 18. I knew from the start x minus 3 was going to be a factor, because what this thing is the original polynomial minus the limit. I plug in 3 to this thing, I get 22. So if I subtract 22 from both sides and I plug 3 in, I get 0. I plug 0 into this polynomial, I plug 3 into this polynomial and I get 0. So x minus 3 is a factor of this polynomial. But this polynomial is the same as that one. So x minus 3 is a factor of this one. So when we do our limit exercises with polynomials, especially cubics, x minus the number that x is approaching is going to be a factor of whatever it is that we're going to be working with. X minus the number that x is approaching is going to be a factor of the polynomial f of x minus the limit. A variation on the limit theme. The limit of f of x as x approaches c equals infinity means that f of x becomes large without bound in the positive direction as x approaches c. Alternatively, we can say the limit of f of x as x approaches c equals infinity means that we can make f of x as large as we wish in the positive direction by making x sufficiently close to c. So let's see. We can make f of x as large as we wish in the positive direction. How large? F of x greater than capital M for any positive real number n that we choose. Now, for this statement to have any meaning, m is going to have to be a large real number. Pick any real number that we want, as large as you can think of. We can make f of x larger than that real number, provided that we make x sufficiently close to c. How close to c does x have to be in order to make f of x greater than this huge positive real number that we've chosen? X has to be within delta units of c, where delta is a function of the real number m. And that stands to reason. The larger that we make m and the larger that we're trying to make f of x, the closer x has to be to c. So this value of delta, which determines how close x is to c, is dependent on how large we want f of x to be. It's dependent upon this real number m. And we'll formulate this concept more precisely right now. Okay, here's the precise formulation. The limit of f of x as x approaches c equals infinity means that given a positive real number m, and we're assuming this is a gigantic real number, there exists a delta where delta is a function of m greater than 0, such that x minus c less than delta implies f of x is greater than m. And again, I'm going to add something sort of in the way of an afterthought, but it's an important point. Remember before in our definition of the limit of f of x, where limit of f of x was some real number L? And we said that x could be arbitrarily close to c, but not equal to c. We're going to stipulate that that's the case again here. X can be as close to c as we want, but these two things can't be equal. And by making x sufficiently close to c, less than delta units apart, f of x will be larger than any real number, capital M, that we pick. Now let's do an example. Okay, this is a nice exercise. Prove that the limit as x approaches 2 of f of x, where f of x equals 1 over x minus 2 quantity squared, is equal to infinity. So the first thing we do is we throw out the challenge. We challenge anyone to give us a real number, capital M, as large as we want, or as large as they want. And we're going to say that we'll make this function bigger than that real number M. So let the positive real number M be given. And then we say let delta equal delta of M greater than 0. And oh, we're in the same situation we were in with the other proofs. We have to pick a delta, and we don't know what delta should be. And again, that's okay, because at this point in the proof, we're not supposed to know what delta is. This is exactly the point in the proof where we figure it out. And we go to our scratch work. And here's what we want. We want delta, a function of M, greater than 0 such that x minus 2 less than delta, and of course greater than 0, implies that our f of x, 1 over x minus 2 quantity squared, is greater than m. And again, just for the record, this is our f of x here. Okay, well, let's go with it. Here's our f of x, 1 over x minus 2 squared. And you know, right at the outset, there are a couple of ways that we can go. Our proof should involve the absolute value of x minus 2. And what we have here is x minus 2 squared. Well, wait a minute. We had two definitions of absolute value of x, right? And one of the definitions, absolute value of x, is the square root of x squared. Well, we want absolute value of x minus 2, and we have x minus 2 squared. So let's see. Absolute value of x minus 2 is the square root of x minus 2 squared. Well, if I took the square root of the denominator, I'd have absolute value of x minus 2. But if I take the square root of the denominator, I better square the whole thing back, right? So I think that's what I'm going to do. I'm going to take x minus 2 squared, and I'm going to do the square root. So this is now the absolute value of x minus 2. Ooh, but I changed the value of the overall expression when I computed the square root. So I guess I better square it back again. So what's inside the parentheses right here? Absolute value of x minus 2. And it's squared. Now, I guess there were other ways to do that. That's just the way I chose to explain it. And let's see. Absolute value of x minus 2 is less than delta. So I ought to be able to relate this expression with 1 over delta. Or let's see. I have absolute value of x minus 2 squared. So I ought to be able to relate this with 1 over delta squared somehow. And let's reason on this. X minus 2 is less than delta. So absolute value of x minus 2 squared is less than delta squared. The numerators are the same. They're both 1. This has the larger denominator. So this expression is going to be smaller than that expression. So my inequality will go that way. And right now, I'm going to pause and think about what it was I was trying to show in the first place. I'm trying to show that I can make this thing bigger than m. Well, I have this thing bigger than something. So why not make this my m? And now I have 1 over x minus 2 squared greater than m. And in order to do that, what did delta have to be? delta had to be such that 1 over delta squared is equal to m, or we can say 1 over m is equal to delta squared. And how do I get delta from this? I just take the square root of both sides. 1 over square root of m equals delta. We got it. Delta equals 1 over square root of m. Oh, this is going to be a great proof. And we're going to bring it to a very quick conclusion now. I'm going to erase the board. Whoops, before I do, I'll encapsulate my scratch work, and I'll write for the reader's sake, end of scratch work. I encapsulate that. If I'm writing this on paper, or if I'm writing this on a larger board where I have plenty of board space, I don't erase my scratch work. I leave it. And my scratch work will accompany my proof when I get done with my proof. Oh, this is going to be great. Okay. So given x minus 2 absolute value less than delta, we have our f of x, 1 over x minus 2 squared. So that's our f of x. And remember the absolute value trick that we did? We took our x minus 2 squared and we did the square root of it, and then we squared it right back. And we did that so that we could get this in terms of absolute value of x minus 2. Square root of x minus 2 squared, that is absolute value of x minus 2. Okay. Now, we have something involving absolute value of x minus 2. But x minus 2 is related to delta. So I'm going to compare this with 1 over delta squared. And remember, delta is larger than absolute value of x minus 2. So delta squared is larger than absolute value of x minus 2 squared. We have two quotients. The numerators are the same. This is the larger of the two denominators, so the quotient will be smaller. And now I'll just take what delta is equal to, 1 over square root of m. We showed that our function f of x is greater than m. That's exactly what we wanted to show. And for the sake of my readers, I'm going to recap what it was that we just showed. I told them what I was going to tell them. Then I told them. And now I'm going to tell them what it was that I just told them. So what did we have? X minus 2 less than delta implied that our function f of x was less than m. Hence, the the limit as x approaches 2 of f of x equals infinity. Bravo. Now there's one more variation on the limit that I'd like to do, and I'll get to that right now. Okay, one more variation on the limit theme. The limit as x approaches infinity of f of x equals the limit L means that as x becomes large without bound in the positive direction, f of x becomes arbitrarily close to L. A little bit more precisely, we can say the limit as x approaches infinity of f of x equals L means that we can make f of x as close to L as we wish simply by making x sufficiently large in the positive direction. So how close would we like to make f of x to L? Within epsilon units. And how large do we have to make x in the positive direction? X has to be greater than some real number m, some positive real number m. Now, let's define this more rigorously. Here's the more rigorous definition. The limit as x approaches infinity of f of x equals the limit L means that given epsilon greater than 0, there exists a positive real number m, where m is a function of epsilon, such that x greater than m implies that f of x minus L absolute value is less than epsilon. We can make f of x minus L less than epsilon, provided that x is sufficiently large. And this real number m is a function of epsilon. So let's do an example. Here's a nice one. The limit as x approaches infinity of 2x plus 5 over 2x equals 1. So here's our limit. Here's our f of x. And here's our proof. And what do? We say let epsilon greater than 0 be given. So we toss out the challenge. Pick a positive real number epsilon. I don't care how small it is, we can make these two things within epsilon units of one another. And now x is approaching infinity, so we have to have our m. Capital M is a positive real number. Oh my, I don't know what m should be. Not to worry, we go to our scratch work, right? Okay, scratch work. We want capital M, function of epsilon, such that x greater than m implies that what? F of x minus our prospective limit is less than epsilon. So here is f of x. Here's my limit. Okay, now let's play around and see what we come up with. We take our f of x minus our limit. And the first thing I think we should do is just combine those terms, get a common denominator. And what have we? Absolute value of 5 over 2x. X is approaching infinity. It's got to be positive. So there's really no need for absolute value bars there. We just get 5 over 2x. And let's see. We're under the assumption that x is greater than m. So I ought to be able to replace x with m here. I don't know what it's going to do to the equation or inequality, but I'm going to replace x with m. And let's see. X is the larger of the two numbers. So 2x is going to be the larger of the two denominators. Ooh, do I really want that? X greater, yes I do. 2x is the larger of the two denominators. So, oh crud, hold on a minute. Forgive me, I just had to get my wits about me. X is larger than m, so 2x is larger than 2m. This expression has the larger denominator, so it's smaller. But this is what we were trying to do. We're trying to get this expression, f of x minus 1, we're trying to get it less than epsilon. Well, we've got this thing less than something. Let's make this our epsilon. So let's see. Epsilon equals 5 over 2m. And that means that m is equal to 5 over 2 epsilon. Okay. M equals 5 over 2 epsilon. I got exactly what I needed from my scratch work. If I'm doing this on paper, I don't erase it, I save it. I turn it in with my submitted proof. I'm only erasing this because board space is hard to come by. And I have to get new board space. But if I'm doing this on paper, I save my scratch work. Okay. So let's see. Given x greater than m, we have our f of x, 2x plus 5 over 2x minus our limit 1. and that's equal to 2x plus 5 over 2x minus 2x over 2x, which gives us 5 over 2x absolute value. But that's the same as 5 over 2x because x is going to infinity, hence x is greater than 0. Okay. Now, x is greater than m, so if I replace x with m here, this is the larger denominator, so this expression will be smaller. And what is m? It's 5 over 2 epsilon. And when we cancel everything out, we get epsilon, which is exactly what we wanted to do. So let me summarize that. I did what I was supposed to do. Now, let me just explain to those who are watching what it was that we just did in case they missed it. We started out with x greater than m, and what did this do? It caused 2x plus 5 over 2x, our f of x, minus 1. So this is f of x minus L. It caused this difference, f of x minus L, to be less than epsilon. Hence, limit as x approaches infinity of f of x equals our limit 1. Bravo. Well, that's all for limits today. In the next installment, we'll have some classic theorems of limits that we'll need for some high power analysis.